Thank you. Yeah, I must say it is quite amazing to see other presentations that actually mention Verilator. It's quite wonderful. So I'm here to talk mostly about version 4, and I must say that we've kind of been creeping up in version numbers, and about a year ago we realized we're about to overflow a major digit, so there has to be something in a new version if you're going to overflow a major digit, right? We weren't quite sure when that would happen, but so about a year ago we started some of this work, and then this talk came up, and it's like, okay, now we have a deadline. I have to have it checked in and all ready to go for this meeting. So thank you for giving me a deadline, getting stuff done. So version 4. So you can guess what the main item is, multi-threaded, but there's some other things in here too. But first, I'll start with an introduction for those of you that haven't heard about it, and what's it good for, what's the point. I'll talk about version 4, what are the main things in it, talk specifically about how we're doing multi-threaded, some interesting algorithms, just a super high level, what's going on, what does it do, give you some benchmarks, why would you care about any of this, put some shame to some of the commercial people, because I love doing that. And then conclusions, and for the most part, unless there's something, really quick question related to a slide that is like a typo or something, you just hold your questions till the end just to get through everything. So first, introduction. So Verilator is really more of a compiler. It's more like what you'd think of as GCC, but for Verilog and System Verilog. What it does is it reads in your normal System Verilog code, and it effectively does what's more like a synthesis and spits out C++ code you would then run through GCC or CLang or Microsoft Visual C, God forbid, or any of those other compilers to get a binary. And it'll then run your simulation. So because it's more of a synthesis tool, it follows more of the synthesis subsets. So the downside of that is it ignores things like time delays. It doesn't have the concept of a time wheel. Your code is the time wheel. But the upside of that is it ignores things like time delays, which means it's actually very fast. It's much more of a cycle-based, although it does have some features that are not purely cycle-based. The other thing is it's really a two-state simulator. It has some special algorithms that go through and can recognize tri-state buses, although those are now becoming relatively uncommon except for off the chip. And it doesn't do x's in the sense of x as an unknown. What it does instead is it randomizes the value. And if you've ever done reset testing, you actually know randomizing values is a much, much better technique than treating x's, because x's never propagate the way people think they propagate in Verilog. And there's been a lot of papers on this. It's much better to randomize. It'll create a C++ or System C wrapper. You can then instantiate it in your own C++ classes. And if you're doing something really fancy, like let's say you're doing a video driver, you could then have your C++ cast, take that frame buffer, actually put it on your screen, for example. So that has a lot of interesting applications for this that in a regular simulator you'd have to hook up in all sorts of really ugly ways through sockets or horrible things. And again, it's creating its own internal interconnect. Some people think what it does is it takes Verilog, and then what's a module Verilog will become a C++ class, sort of one-to-one. It actually did that way in when it was originally invented back in digital to actually do some digital alpha design. But it hasn't done that for quite a long time. It's much more complicated than that. So what's the simplest way to do it? I'm going to skip all the installation instructions. You can look that up on the web, on the wiki page, and I'll have the link at the end. The first thing I always recommend is lint your code, so just Verilator. And the syntax, it understands both what you think of as traditional simulator syntax like -y, and it also understands more GCC-like syntax. I actually like the GCC syntax better. Either work. So anyways, pass lint only and turn on all warnings and pass in a Verilog file, and it'll find all the submodules and all that and spit out a bunch of warnings. As far as I know, Verilator is the only tool that actually has lint-like capabilities. So if you're not using Verilator, you'd have to go to a commercial tool. So for example, here's a little module. You can split it in, and you can probably guess what it's going to complain about here. It'll say basically you have this should normally be an arrow equals. If you don't put arrows equals, it'll simulate fine, but as you know, there's potential races and all these other things. There's things like width warnings and sort of all the common errors that you would hope a linter would find. And this is another area for improvement. It does a pretty good job, but there's always other warnings people come up with that are useful. Where Verilator was originally designed, and the way most people are using it is more as, again, to synthesize into C++. So you just say Verilator cc and convert.v, pass it in your Verilog file. And what'll come out, super simplifying it, of course, has a lot more verbosity around it, but is basically a C++ class. And there we go. And you see that I have my input clocks and data and an output, and these just become bool for the clock, and because this is 32 bits, it becomes a uint32, likewise for the output. And then these two functions, eval and final. And your model would just come in and call evaluate every cycle, and then when it's done, it would call final just to do a bunch of cleanup, like assertions, things like that. So, one of the amazing things, and I wrote this actually before this talk, it's now amazing to see not only people talking about Verilator, but the commercial IP and open source IP are now providing Verilator support. So for example, your cell phone, almost certainly part of the design of your cell phone was done using Verilator. The code you actually get from the major cell phone IP provider includes Verilator support out of the box, at least for their more recent cores. The same with the other sort of, let's say, older four-letter IP provider company. And open source, there's been several presentations already where the open source people supporting Verilator. And it's also used by most of the leading CPU designers. There's a number of reasons for this. One is, it's not just that they like the open source aspect. It can actually do things you can't otherwise do with a commercial simulator. Again, it's faster. And the other big benefit is, say you're on a laptop and you're on an airplane and you want to run a simulation, you can do that with Verilator. You can't do that with a commercial simulator. You need a licensed server. So let's talk about version 4. First, I'd like to thank everyone that's contributed. And this is over years. It's not just most recent. And there's probably at least 20 people in this room on the list. And hopefully I didn't miss you. If you do, I apologize. I won't read all the names, obviously. But thank you all. Even people that send in bug reports, well, I don't necessarily like getting bugs. I understand they happen, and it is appreciated even if you take the time to say, the following didn't work for me. Even better if you give me a patch. But even just to say, thank you, that's great. One of the changes that was just submitted only about 3 or 4 weeks ago is LXT support. So you now can run GTK Wave on it. So that helps some people. There's been a bunch of single-threaded performance improvements. We'll see some of those in a minute. Verilator never used to have any runtime options because it assumed the user code was doing all of the, that C++ class. It now has some standard options to simplify people having to write some of the code they would have otherwise had to write every single time they write a simulator. And then multithreading, which I have a whole section on, which is here. So what is the problem with multithreading? Well, conceptually, the way Verilator works is it pulls in your Verilog code and does all sort of the parsing and elaboration, all this stuff you have to do that's just kind of parsing related. And then eventually what it comes up with, you can think of as a bunch of nodes in a graph. And this is a graphical figure, so forgive the massive oversimplification. But imagine you have some code that is doing some assignments, some code that's doing functions, maybe another thing that's doing and of a bunch of operators. And you can form a huge graph that basically connects all of these different operations together. So for example, this assignment then feeds some AND gate, which feeds some other assignment, et cetera. So you basically build a whole DAG, a directional acyclic graph of the code flow. And of course, it's really more complicated because there's other clock domains and all that, but let's ignore that for a minute. And we call these microtasks. So I have all these bazillion microtasks. And the way Verilator used to work, and still does actually in single-threaded mode, is it does through a bunch of algorithms, it figures out a way to order all these tasks in sort of one long line in a way that it thinks minimizes cache behavior and other sort of characteristics that makes it fast. But to get multi-threaded, of course, we have to be a little more sophisticated. So what it does now is it builds something called macro tasks. It tries to group together these little micro tasks based on how long it thinks each of these is going to take to run and how long each of the interconnected edges it thinks is going to take in terms of communication costs. And it builds a bunch of these where the number of these tasks is roughly 10x the number of threads you want. So let's say you're going to run on a 4-threaded machine, it would want to get about 40 of these. We've played a little bit with that number, but it's around 10x. So I now basically have what before would have been, in a real design and large design, you'd have as many of these as gates potentially. You might have, a million of them. So now I'm down to 50 of these boxes. The next challenge is what it does is it takes these tasks and it linearizes them within that macro task. So now I have these boxes that are effectively, you can think of each of these as what might eventually become a thread, and I've sort of organized this function, then do this equal, then do an and, then do another equal, etc. Likewise, I've done that for the other tasks. And then these edges, which are the communication, are now between macro tasks. So I sort of simplified the problem. Now I have a directional acyclic graph of only 50 nodes, something much smaller. Then the final thing I need to do is I'm going to statically assign these macro tasks onto threads. So in this picture, I have 2 threads, for example. Okay? And it's just through heuristics decided that one macro task will run on thread 0, another macro task will run on thread 1. And then all these edges become cases where it has to do synchronization primitives between the threads. Now, what's interesting about this was not the first thing we tried. The first thing, actually, there's several things we tried and failed. The first most obvious thing was take these macro tasks and put them on just runtime onto a list and say, here's 50 tasks. A CPU picks up when it's free. It says, what's the next best thing to work on? It works on it. You'd kind of think that that would be the best, right? Because you'd think that, well, what's going to happen otherwise is imagine this thread 0 takes a super long time. And even though I think it might run like this red kind of goes way off the bottom. And I don't have equal allocation. Thread 1 basically gets finished right away, and I get horrible utilization of the threads. Yeah, that's true. But it turns out, from at least the designs we studied, all the time is basically in cache effects. If I dynamically move this every cycle between cores, the data migrates from one core to another across the caches, and you basically get screwed in terms of cache thrashing. So at least for right now, all the partitioning is static, and for the models we've tried, that's actually better performing. But that's definitely an area for future improvement. So there's lots of cases where we made certain assumptions. They seem to work okay, but there's lots of room for improvement. And you'll see that in some of the final slides. But we're still doing pretty good without more sophisticated assumptions. So what did we get with this? So I'd like to thank Packet Architects, an IP provider. They actually gave us a very large model. We actually looked at using some, and we did use some of the open cores that are available and RISC-V cores that are available now. The problem we had, and they worked okay. The problem we had is they weren't really big enough to kind of, we really want something in the multi-million gate range, because then we can try out the partitioner. We can make sure that the heuristics scale, they're order of n rather than order of n squared, things like that. So this is kind of the biggest thing we had access to. So that's why they decided to benchmark, and of course mileage may vary. And this is compiled out of the box. This is not, we didn't, and actually right now Verilator doesn't have any knobs to tune its multi-threaded implementation. So long term we certainly will add those, but right now if you download if you purchase their IP, you run it through Verilator, these are the results you get. There's no special tweaking going on here. So, on the particular machine I was using, I only had access to 2 of the big 3 licenses. I apologize. The other big 3 you can imagine is somewhere similar. Also, you're not really supposed to benchmark the commercial simulators. So by not putting a third person here, if you talk to their salesman, they can make you believe that their simulator is better than any of these. It's not. Anyways, so these are 2 of the big 3 running the simulator. This is to scale, but I didn't want to show the numbers again because I'll get in trouble with some of the commercial people. So this is Verilator 3.926, which was, I think, 2 releases before version 4. It's a little bit better, I don't know, 10% or something. It's great. Price is, of course, a lot better, but it's basically as good as the commercial simulators.
And this is all single core?
This is single core. This is all single threaded. So version 4, we made a number of improvements, especially related to how we break up large always blocks, some of scheduling improvements, a number of things. This gives you roughly 30% more performance. So we're now about 40% above any of the commercial off ratings. On this particular benchmark, again, mileage may vary. But can we do better? 30% is pretty good. We can do better than this, right? So let's go to threads. This is on a 4-threaded machine. Oops, sorry about that. I guess we better renormalize. OK, so on a 4-threaded machine, we're getting 1.9x performance improvement. When we got to this, I was amazed. I never thought we'd get a 2x on 4 threads. I really didn't. And again, this is without particular tuning. So I was quite happy when we got to this. So 1.9x is good, but can we do better? So using a tool we'll talk about in a minute, we benchmarked this. It turns out that, for those of you that are architecture geeks, which probably a lot of you are here, if you look at the Intel architecture, right, there's what is a CPU to Linux may not really be a CPU. It could be a hyperthread, or it could be a CPU on a socket that's on a different socket. So it just happens that the default, at least on the Linux version I was using, what it gives you is it gives you CPU 0, 1, 2, and 3. It just happens that on the system I'm using, and a lot of systems, those are 2 CPUs on this just happens 8 CPU system, and they're on 2 different sockets. So that means anytime I'm doing a semaphore passing data between 0 and 1, I have to cross the socket boundary, likewise between 2 and 3. That's not great. Oh, by the way, this is LS CPU output, which is very useful for this. If I then use NUMA control, I can say which particular threads and CPUs will be assigned together. So instead, if I use 0, 2, 4, 6, I'll get 4 CPUs on this 8-core machine, but they're all in the same socket. So let's run the exact same benchmark. The only difference is I'm going to run it through NUMA control. Whoops, and I go past my slide. That gives me an additional 30%. I'm now at 2.5x. Hey, that's great. On a slightly larger command line, you get 30% more performance. I'll take that. But can we do better? So this is actually a different machine because I need more CPUs. This is running on a, actually turns out 48-core system, dual socket. This is the same benchmark. So here's my 4-thread number. I can keep going, 6 threads, nice, great linearity. 12 threads, this of course is double the number of cores. I'm doing pretty good. I'm at 5.5x, but I'm sort of reaching that point of diminishing returns, which you would expect. But this is still pretty good, 5x performance improvement, 5.5. For 12 threads, there's a lot of cases where I would certainly do that. I would throw an entire machine at some of our full chip simulations that take a week very happily. If I push it to 24 threads, well, there's a little bit there. I'm not getting a whole lot. I'm getting killed by Amdahl's law. If I push it to all the cores, 48 threads, what happens is I now push, when I was at 24 threads, everything was on one socket. Once I go to 25 threads, or even 48, I now have that cross-socket communication. And you see, it killed me, right? I take this penalty, it goes way, way down. So it's all about moving the data between the different threads, which is intuitively what we'd kind of expected, but is definitely the case. So basically, the more cores you can get on one socket, that basically is what will limit your performance, at least until we figure out some new knobs and better algorithms to figure out how to do cache partitioning and decrease communication costs. So one of the tools to look at this, we made something that takes the runtime graph and puts it into a waveform viewer. What this shows you is basically on each of the CPUs, so each of the physical CPUs 0 through 6, so basically there's 4 threads, which of the M tasks is running, right? And you'd have to read a secret decoder ring to know what all these M tasks are. But basically you can kind of see that CPU 0 is kind of busy all the time, and then 2 has some of these idle times, which I showed as Z's because I thought that was kind of cool. And then this is another view of the same thing, so the 4 threads, which M tasks are running. So what you notice is basically there's this period of time when there's only a single thread active. Oh, and by the way, this thing at the top is how many threads are active at a given point in time, right? So there's this long stretch where there's only a single thread that's active. And that's what's limiting the performance. But again, I'm still getting 5.5x on 12 threads. So it's not great that the way that it's doing the static partitioning is giving me this big gap, but it's hard to complain about a 5x performance improvement, at least today, because I'm still happy because there's new code. In a year, it will very much depress me. I'm only getting 5x, and I'll work some more, and we'll do better. So this is 52% scalability. I work for Cavium, now Marvell. We have large 48-core chips and larger. And again, 50% scalability is actually very, very good for the average program, your average program that doesn't totally parallelize like some numeric applications. So 50% is quite respectable. So that concludes the main part of the speech. In general, I would obviously like to encourage Verilator. That's why I'm here. There's been continued improvements for 20 years. It's now more than 20 years old, which is kind of scary. And it now runs faster than major simulators. Other commercial simulators do, of course, have multi-threaded support, some of them anyways. I've had mixed result with it. I think this stacks up better than them, but obviously benchmark yourself. Open source helps you. I'm at this meeting, so everyone already knows that. But it lets you run on laptops, which you can't do otherwise without licenses. You can get bug fixes, because of course you have the source code of Verilator, so if you have some problem, you can fix it easily. And for those of you with commercial licenses, it always helps during a license negotiation to say, well, actually, primarily we're using Verilator, but, knocks a few $1,000s off each license. I didn't say that. Turn off the camera. And people always ask me, well, don't you get rid of commercial simulator? No. I mean, the point of this is it's a supplement, really. Maybe you do need a couple of licenses, but in general, there's lots of things Verilator doesn't do. It doesn't do things like PLLs, any of the analog stuff, any gate back annotation, or any of those kind of things. You always need a commercial simulator for that. And actually, to be honest, the more simulators you run on, I find there's actually bugs related to simulator and code portability and things like that. It's always good to run on more than one simulator. Also at Veripool, which is where Verilator is hosted, is Verilog mode for Emacs. Probably most people are familiar with this now, but basically the idea is you have your Verilog code down here in Emacs. You just hit a magic key, it expands it, and then what comes out is totally valid Verilog. So this is kind of like a little virus that lives in your Verilog code, and people that have the magic Emacs Verilog mode can just take in this code, expand it, and be a lot more productive. People that don't, they're totally fine. They don't have to run the tool. And if you look at a lot of commercial IP, again, some of the leading IP providers provide code that does this. Some of the utility has been moved into the system Verilog language. This was originally far more useful before some of the more recent system Verilog features, but it is still useful for a lot of things, and especially the automatic instantiations. You can do .star, but you can't do parameterized .star. If you want this slide set, that is now available. I uploaded it last night. On veripool.org, you can also, of course, download the tool, provide bugs, there's forums, all sort of the normal open source-ish stuff people come to expect now. Thank you very much.
Yeah, thank you. Great work. Quite a few hands showing.
Hi, Wilson. Thank you very much for this. Good work. A couple of questions. First is, actually, about your day job and getting to develop this. So how does it work? You're a digital designer, or you're doing tools for the company, or?
Yeah, actually, I'm a lead architect at Cavium. So for those of you that know, like the Octeon, TX, and Thunder product lines, so that was basically my chips.
Yeah, great.
And previous jobs, I had a lot more time to do Verilator because I was more kind of closer to RTL and synthesis. Okay. Now it's actually almost 0%. It's basically after hours and that kind of thing. I mean, they don't mind if I work on it, but I have so much other work that I feel too guilty doing it during hours.
How big is the very active development base now, or the developer base, rather?
Yeah, I mean, so Multithreaded was actually done by someone else. Actually all the work, really. The LXT stuff was by someone else, so I would say probably 70-ish% is done by other people. So 2 or 3 main people, and of course, as usual, lots of other people submitting patches, which is very much appreciated.
Cool, cool. My next question is about Coco TV support for Verilator. Do you think it's going to happen ever?
Sorry, what?
Coco TV. Oh. So basically, the VPI interface to go in, and you've got like a little scheduler in Python that goes through and I don't know, like enables access into a normal Verilog design through the VPI ports, and then you can do verification in Python. You must. Do you know Coco TV? Yeah, sure. So I think at the moment it doesn't work with Verilator because Verilator optimizes away a lot of the stuff internally, or perhaps doesn't have all of the nets available via the VPI interface. Is that more or less right?
I don't know.
Okay, all right.
I mean, it does eliminate nets. I don't know about the specific issues.
Okay, that's cool. I'll talk to you about it after.
You can take it offline.
What happens with the commercial tools when they go multi-threader? What's their acceleration across 4 threads on the same socket, or 24? Do you just have some quantitative comparison on that part?
I shouldn't comment. I mean, some do better, some do worse. In my experience, you always need several AEs to get it working. Let's leave it at that. You should contact your vendor. They all have multi-threaded solutions. This will do very well comparatively. Let's leave it at that. I don't want to get, I'm good friends with a lot of people that do simulators. It's not, I mean, it's healthy competition, right? I don't want to.
Hi. When you described how your initial approach didn't work, where you had like a work queue and each thread picking what you call the macro tasks off the work queue, then you ended up with cache thrashing, and then that limited the performance. I'm kind of surprised that even with a static allocation, the threads can remain cache resident. I mean, like most designs I'm simulating seem to use hundreds of megabytes, even a gigabyte of RAM during simulation. I wouldn't expect much of it to remain cache resident.
Yeah, the good and bad thing about Verilator is actually most of the thrashing isn't so much data cache, it's instruction cache. So even though your data set size may be ginormous, the instruction thrashing actually is a bigger deal. So it does somewhat, it's not just the data moves, but actually the instruction cache misses hurt you a lot too. So I think that's what's going on. I haven't actually spent a lot of time benchmarking it to figure out exactly what the ratio is between instruction and data cache thrashing.
Okay, but just to put it in context, what kind of gate count size design were you using for that metrics you presented?
This was pretty large. I'm not sure I should say exactly, but this would be comparable to a significant fraction of a modern technology die.
So like a million gate plus, or?
Might be. And by the way, if anyone has large benchmark, again, we tried to find a really large example that was open source. We played a little bit with the really old Spark that was available, and that's kind of deteriorated due to a bunch of reasons, so we couldn't run that. But if someone has a really big system you want to throw it at, we'd love to have a benchmark we can point everyone at.
With single-threaded, does that still work with multi-threaded? Do you still see the same benefit?
Actually, I haven't. That's a good point. I should have tried profile-driven. With the models I've played with, like this one's single-threaded because I know I'd played with it a while ago. I think actually compiling for size I think gave 10%, and I think profile-driven gave 25% more. There's no reason it should be similar because basically you're just shrinking the critical code section. So actually it might even do better than that. So I would expect similar improvements. But that's a good point. I should have thought of that. I could have had bigger numbers. I'll go try that when I get home.
My apologies if you've been asked this question many times before. I hereby apologize for that. Is there any chance that Verilator will take on VHDL at some point?
So if you look at the forums, so maybe 5 years ago there was someone that was starting support for VHDL. They got waylaid into other projects and only had a very simple repository. And then there's another group that of 2 people, 2.5, I guess I would say, people that are kind of brought up the charge again about 6 months ago, and they have a branch that is just starting to show signs of life. So if people can contribute or maybe even show them encouragement, I'm sure it will help greatly.
Other questions? Yes.
So the first thing I'd like to say is thank you. Thank you. And I love Verilator, and I use it for almost every. I'm sure others would agree with me.
I paid him.
The next thing I would the next thing I'd like to comment is on the VCD support for Verilator. That has usually been one of the most difficult parts of any Verilator simulation, is dumping the logic out to disk during the simulation. I saw you mention something about, what is it, LTX2 support? Would you like to spend a moment to discuss that and explain that for me? And then before I let you start, let me just say for everybody else, Verilator does support formal constructs.
Yeah, so as I hinted at, maybe about a month ago, someone started LXT support, and they managed to squeak it in for the version 4 release. So LXT2 is a format that GTK Wave supports, and it's a GTK Wave native format. So that gives you sort of more compressed dumps, so higher performance because you're not as I/O bound. So I definitely recommend that as long as you're using GTK Wave. There's another newer GTK Wave format that supports structures and things like that. That support isn't there yet, but hopefully someone will take up the charge and add that. So that's kind of the next step, is not only have faster traces, but also be able to trace some of the more system C-like things, looking like structures and looking like enums, and as opposed to just looking like hierarchy. So that would be kind of nice. Unfortunately, ideally, and this came up, I don't know, I was in a brief working group maybe 15 years ago to replace VCD with something else standardized that never went anywhere. There is no multi-vendor standard other than VCD, unfortunately, which is really stupid in my mind. But if you're a commercial vendor and you have your simulator and you have your waveform viewer, it's not really in your interest to provide something open source, which is unfortunate, but is what it is.
Just going back to LTX2, so you can compile up system Verilog, you have enumerated types, structures and stuff like this, and you can see them on the screen. It's not just ones and zeros.
No. So right now, so LXT2 is really a more compressed version. Again, I didn't write the code. My understanding, and this might be wrong, is LXT2 is really a binary format that has similar capabilities to VCD. But then GTK Wave moved on to a newer format. Does anyone know the name?
FST, I think.
Thank you, FST, which does support enums and structs and all that. So this was kind of a stepping stone. I think the hope is to get to the full format and be able to dump everything. We're not quite there yet, but it's a step in the right direction.
Okay, now let's thank the speaker again. Thank you very much.